So for today's chapter exam, we were told to use the last two digits of our VID number. So the last two digits of mine are 8 and 5. So 8 plus 5 equals 13, and since there is no number 13 on the homework, I did 1 plus 3 equals 4, so I got question number 4. Question number 4 reads, learning goal: to understand the relationship and differences between electrical potential and electric potential energy. In this problem, we will learn about the relationships between electric force F, electric field E, potential energy U, and electric potential V. To understand these concepts, we will first study a system with which you are already familiar, the uniform gravitational field. So, for part A, it asks us, find the force Fz on the object of mass m in the uniform gravitational field when it is at height 0. And we have to express this in either terms m, z, k, and or g. So for part A, we would use from those selected terms negative m, g, k, because since this is taking place in a uniform field, the force doesn't depend on the object's location. So in reality, we don't need the z at all, and we use k instead for the equation. Part B asks us, now find the gravitational potential energy Uz of the object when it is at an arbitrary height z. Take zero potential to be at position z equals 0. Keep in mind that the potential energy is a scalar, not a vector. So, for part B, we would express this in mgz due to it being in scalar instead of vector. Part C asks us, in what direction does the object accelerate when released with initial velocity upward? So, since the initial velocity upward is, the initial velocity is upward, the direction that the object will accelerate will be downwards, due to it having to be opposite to what it opposite to the direction it began as. Part D asks us, find Fz, the electric force on the charged particle at height z, and we have to express it in terms Q, E, Z, and or K. So for part D, we would do the equation negative Q, E, K, and in this equation, we're using E as a vector. And also, the force on the particle charge Q in the electric field is equal to the equation E equals negative E K, which can also be given as F equals QE. Part E asks us, now find the potential energy Uz of this charged particle when it is at height z. Take zero potential to be at position z equals 0. So we are using this, using the terms Q, E, and Z, which for the answer to the equation is the same thing. So it would literally just be Uz equals QEZ. So part F asks us, in what direction does the charged particle accelerate when released with upward initial velocity? So, since the particle is charged, it would have to either be upwards or downwards, depending on the charge, because the charge is the main factor in determining what direction it will go. So, for instance, if it was, up is like positive, it would end up going downwards because it goes the opposite direction that the positive charge goes. So for part F, it would be up or down. For part G, it states, find the electric potential V of the uniform electric field E equals EK. Note that the field is not pointing in the same direction as the field in the previous section of this problem. Take zero potential to be at position Z equals 0. So instead of doing QEZ for this equation, for part G, we would instead use negative EZ. Question H asks us, the electric field can be derived from the electric potential just as the electrostatic force can be determined from the electric potential energy. The relationship between electric field and electric potential is E equals negative nabla V, where nabla is the gradient operator. And this equation is given, which is nabla V equals the derivative of V over X I plus derivative of V over Y J plus derivative of V over ZK. So the partial derivative V over X means the derivative of V with respect to X, holding all other variables constant. Consider again the electric potential V equals negative EZ corresponding to the field E equals EK. The potential depends on the Z coordinate only, so V over X equals V over Y equals 0, and V over Z equals V over Z. Find an expression for the electric field E in terms of derivative of V. So for this, for part H, to have an expression for the electric field E in terms of derivative of V, we would use E equals negative the derivative of V over derivative of ZK. For part I, the question asks us, a positive test charge will accelerate towards regions of blank electrical potential and blank electrical potential. So, for this question, for part I, the positive test charge will accelerate towards regions of lower electric potential to it would accelerate towards regions of lower electric potential and lower electric potential in order to equilibrium, because since the positive is a higher charge, it would move down to the lower charges to equal them out. Part J asks us, a negative test charge will accelerate towards regions of blank electric potential and blank electric potential, or energy. So for part J, instead of rushing to both lower, it would rush to higher and lower, like the reason before, in order to equal out all the regions so that they're all in equilibrium.